Hi, I'm Rick Hedgeman. I'm your professor for Mgt602, Production and Operations Management. We will spend 2 days going over this particular presentation on quality tools and control charts. It's not a long presentation, it's about 46 slides, but it does have some important content. So let's go ahead and get started and see where we go with this. So one of the first tools that I really want to introduce you to is called the cause and effect diagram. It goes by multiple names, including, because of its appearance, I think that's obvious, the Fishbone diagram, also sometimes called the Ishikawa diagram, named after a Japanese quality engineer named Kaoru Ishikawa, who was prolific during his career. So let's see what the cause and effect diagram is. It is a simple diagram where we have an effect. The effect is ordinarily one of two things. It is either a problem or a challenge that we want to be able to solve or conquer, or it might be an opportunity that we would like to be able to get in on. And so whether it's a problem or whether it's an opportunity, that's the effect. Ordinarily speaking, we try to state that in the positive. What do I mean by that? I mean, if you're, say, a time-definite delivery service such as, FedEx or Flying Tiger or DHL or UPS, you might be suffering from late deliveries, especially during holiday rush seasons or something like that. But rather than say reduce late deliveries out there for the effect, you might say increase on-time deliveries. Now, those might not be precisely equal, but the point is that you can usually state the effect in the positive. There is a human result that comes from that. And the human result is that, generally speaking, people function better when they're focusing on the positive than when they're focusing on the negative. When they're focusing on the positive, ordinarily speaking, they're more likely to derive legitimate solutions, as opposed to when it's phrased in the negative, they will, ordinarily speaking, be pointing fingers, including at other people, which is very uncomfortable, or worse still, at themselves, which is maybe the most uncomfortable thing, because depending on the culture of the organization, pointing a finger at yourself may render you vulnerable to challenge from others, or may render your job at risk, or something of that sort. So generally speaking, we try and state the effect in the positive. Everything else that you see on the chart are, keyword, potential. They are potential causes of the effect. Of those potential causes, some are probably very real, some are probably trivial, and some may not even exist, but they just are things that you want to consider. So, typically speaking, what we do is we divide the potential causes into a few major families of causes. Materials, methods of work usually, or methods of performing something, equipment or machinery, we can call that infrastructure if we want, and the human ecology that's involved, the people that are involved. So those are the four traditional categories: materials, methods, machinery, and manpower. So you can see that those are probably traditionally called the 4 M's. Now, of course, those have been modified as the tool itself has been become one that's in more common use, and that people have adapted to other uses and so on. So now we're more likely to say something like materials, methods, equipment or infrastructure, and the human ecology or people power. Now, we're also likely to include at least 2 other categories. And those 2 other categories are the environment and measurement. Now, by the environment, I don't necessarily mean the natural environment, although that could, of course, be something that could be there. It may be the political climate in the organization. Or it may be, for example, that you're in an organization that employs a clean room. So in a clean room is one where you have very sensitive equipment, usually very high priced. The environment inside that clean room has to be controlled. Temperature, humidity, things of that sort. Dust levels have to be tightly controlled. My brother, who was a civilian employee for the military for decades, worked in clean room environments primarily. He designed drones. He was designing remote control drones back in the 70s when he was at the Naval Weapons Station in Nevada. He was running the computer system for the Naval Weapons Station in California afterwards. He was working on the Pershing missile program in the early 1970s at one of the Army depots in Colorado. So he was often in a clean room environment. So it could be climate or something of that sort, but it could be political climate, the culture of the organization, so to speak. And then on measurement, the idea behind measurement is that if you can't measure it, how do you know if you're getting better or you're getting worse? How do you know if you're winning or you're losing? So we almost always include those categories of environment and measurement. As for the other categories, those will depend on the sort of application that you have. And of course, relative to any particular problem or challenge, there could be some very specific sorts of categories that you would like to include. So cause and effect diagram, here's an example. This is one where you're sitting in manufacturing. Well, in manufacturing, we often have more categories or different categories, and you can see what those are in this one. Similarly, if you're talking about service industry applications, you might be dealing with things like this particular cause and effect diagram or Ishikawa diagram. And there's a video for you on improving the Fishbone diagram. Now, we're not going to go over that video in this course, but let me tell you that there are some good ways to approach construction of the cause and effect diagram or the Fishbone diagram. And to do that, I'm going to pull back a few slides. So one of the things that you would ordinarily do, and this could be an individual tool, but it's more likely being employed in a team environment. And in a team environment, the team that's been pulled together is a team that's been pulled together to address that effect that's sitting out there, the particular challenge or problem that you face, or the opportunity that you hope to be able to get in on. And so what would happen is that the team is, ordinarily speaking, drawing on their own knowledge of the circumstance. They are probably very familiar with the processes. That's one of the reasons that they've been selected for the team. They are probably, if it's a big enough problem, they're probably cross-functional. They're coming from different areas of the organization or different parts of the plant or something like that. And so what will happen is that they will essentially brainstorm and bring their explicit knowledge to the table, and they will say, well, materials. So among materials, here are some of the things that could contribute to that effect. We have this thing right here. And this arrow is facing the wrong direction. It should be facing inward, but basically the idea would be. And among that thing right there, here's some other things. And so you could have, for example, back in the 1980s, there was an aircraft manufacturer named McDonnell Douglas. McDonnell Douglas made a plane called the DC-10. The DC-10 was having some particular challenges. Literally, it was having engines fall off in flight. And so what did they trace that to? Well, ultimately, what they traced that to, I mean, your effect would be engines are falling off. How do we stop our engines from falling off? But there are a lot of different causes, potentially, of the engine falling off. What they were able to trace it to, in large part at least, was that there was a mismatch between the nuts that screwed onto the bolts that held the engines onto the aircraft. So in other words, the nuts on the bolts didn't fit well enough. Well, if they fit in a way that it's too tight, what happens is that you can produce metal fatigue. It weakens the strength of the metal in the bolt or in the nut itself, either way. And you can have that snap in flight caused by vibration or something like that. And therefore, a few of those things happen and you lose an engine, plane goes down. Or plane is grossly damaged or you lose your load, whatever the case may be. So as another possibility, you had the idea that those things fit way too loosely. Now what happens if they fit too loosely? Well, if they fit too loosely, then the plane has a chance of having the nut work its way off or become loose from the bolt. Not even necessarily work its way off, but become loose from the bolt as you're in flight. If enough of those things happen, then the vibration begins to happen. Once the vibration starts to happen, then of course you're beginning to work on the bolt and introduce breakage in the bolt, or work the nut the rest of the way off. Now, those were the causes that they identified as being most central to the problem. Another example was the Space Shuttle Challenger. Now, when the Space Shuttle Challenger exploded shortly after takeoff, I was watching that live. I was living in Rochester, New York at the time, working at the Rochester Institute of Technology. And like many people, when I saw that happen, I thought maybe there was just something natural that I was looking at. Well, it wasn't natural. The Challenger was literally exploding and lives were lost. So what did we have? We had the Challenger exploding. What caused the explosion? Because there are many potential causes. What they found was, in fact, that it was a gasket, something called an O-ring, a gasket that was intended to be between two different parts to seal that part. But instead, that gasket, under the launch conditions that they launched under, when it was too cold, that gasket or O-ring became brittle. And when it became brittle, it didn't really function in the way that it was supposed to function. Therefore, the seal wasn't what it was supposed to be. Therefore, you ended up with an explosion. Space Shuttle Challenger, you lost the entire space shuttle. That was a big setback, as you can imagine, to the space program at the time. Now, Morton Thiokol was the manufacturer of the O-ring, and Morton Thiokol received a lot of blame for that. It was actually not Morton Thiokol's blame to be assumed, because Morton Thiokol and all of the specifications that they had and everything that they produced said, do not launch under these conditions because this O-ring could be too brittle and we could have danger to the integrity and the safety of the flight. The launch team made that call. That is, NASA itself made that call to go ahead and launch, and it cost lives. But those were the eventually identified causes of what went wrong for the space shuttle, for the engine dropping off McDonnell Douglas DC-10. But, there were many other possibilities that could have occurred. So what do you want to do to make this better? One of the things you want to do to make this better as you go along is, once the team has determined what they think the cause and effect diagram should be, put it on a huge piece of butcher paper or something like that, or distribute it electronically in the departments, in the areas where this process is being carried out, or where it's affected, or where this can happen, this cause. Leave things like markers around, like a blue marker, and let it be annotated. And then move it to the next department. Let it be annotated again. The next one, let it be annotated again. Blue marker, red marker, green marker. Afterwards, you have an opportunity to see more closely what people knew, how much they knew, where more explicit knowledge was coming from, and you're able to refine and improve your chart. Another possibility might be that you have exactly the same categories across the top as you do on bottom, except on top you might have things to help you conquer the problem or take advantage of the opportunity, whereas on bottom you may have roadblocks. So you might do something like that. You might be able to time sequence things. So there are lots of possibilities you can use your imagination to try to employ to improve the function of these control charts, or these cause and effect diagrams. Another straightforward tool, at least it's simple in concept, just as the Fishbone diagram is called the Plan, Do, Study, Act cycle. Many people refer to it as the Plan, Do, Check, Act cycle, PDCA, as opposed to Plan, Do, Study, Act, which is, Plan, Do, Study, Act, PDSA. And so the idea is actually very simple. It's a common improvement cycle. It's often called a continuous improvement cycle, or sometimes called the Deming cycle or the Deming wheel, called after the person who made it popular. The guru of all gurus in quality management, named W. Edwards Deming, who has now been dead for almost 30 years. He died in 1991. So what we would do is something like this. Let me go back. We start by planning a change in our process that we believe will be to the benefit of the process. We'll produce better quality, we'll make it faster, will improve the process in some way. We make the change that we've planned, probably on a small scale initially, or a pilot scale. The reason that we do that is that whatever improvement we see, if we see improvement, may not be large enough to warrant the sort of investment that it takes to run out the change on a large scale. So it may not be a large enough improvement, a beneficial enough improvement. It may, in fact, not be an improvement at all. It may be that for all of your best intentions, that whatever change you planned actually led to deteriorated performance. So plan the change, do this change probably on a small scale, study the results of the change, and then act upon the change. So when we say study, that is why Deming changed the verbiage from plan, do, check, act to plan, do, study, act. In changing that verbiage, he used the word study. He could have used a word like analyze to imply that it's a very serious consideration of the new performance of the process, or the performance of the process under the conditions where the change has taken place. So it's a serious study, hence removal of the word check, which wasn't taken so seriously. When asked late in his life why he made that alteration, he said, well, may I not also learn? And that was his general attitude toward things, is he was a learner. So plan, do, study, act is ordinarily what I will say. You may hear me slip sometimes and say plan, do, check, act. Plan, do, study, act. So study the results of the change and then act. Act upon what you've learned from the study phase. And when you act, oftentimes that will mean implement on a broader scale. It may mean that that the change wasn't large enough or good enough so that you don't make the change. You go back to whatever status quo was before that. Or you go into another planning phase, right? You go into a continuous improvement cycle, which is what the PDSA cycle is often called, a continuous improvement cycle, where we go through this repeatedly, incrementally changing and improving the performance of the process so that over time we accrue a larger benefit. Now, I believe there's a better way to practice this, and I'll start by adding another word, focus. Focus, then PDSA. So focus would say to do something like the following. Identify specific aspects of your process, system, production, process, whatever it is, targeted for improvement with a clear focus on what is in need of improvement. Once you do that, organize. Assemble the right team that's sufficiently diverse in terms of what they're capable of doing, their competences, and with sufficient expertise and experience in relation to that improvement opportunity. Having done that, clarify the improvement opportunity. What does improvement entail? What is it that you think that will result if in fact you're able to successfully improve the process? Understand the various causes of the problem to be solved, as well as enablers of improvement. That means that you might be using something like the cause and effect diagram, the Fishbone diagram, before you use plan, do, study, act. That may aid your understanding. And then get going on your plan, do, study, act cycle. Now, oftentimes I abbreviate this focus part and just say establish baseline results. And by establish baseline results, that means that before I go into changing the process, I should have a clear understanding of how it's performing right now and what it is. And once I do that, then I should be able to launch into Plan, Do, Study, Act, described as I've previously described it. Now, the way that this has often been practiced at Hewlett-Packard, and I've done lots and lots of consulting in the past for Hewlett-Packard, so that sometimes I call this Edgman's modification of the Plan, Do, Study, Act cycle, is what I used at Hewlett-Packard, especially in Colorado back in the 80s and early 90s. So what would you do? You would initially establish the baseline results, plan the change, implement the change, probably on a small scale, study the results of the change, and then before you ever make any changes on a broad scale, standardize what you're doing. Now, the reason that you're standardizing is so that once you implement any changes, that they are implemented in the same way everywhere they go. In other words, that as you go through, you're implementing the same thing as opposed to thinking that you're implementing the same thing but ending up with 10 different processes. That's different everywhere that you go. So standardization actually is there because you're trying to make the solution itself more portable. Then act, which is probably implement on a broader scale. It could be return to status quo. And remember, this is a continuous improvement cycle. So now you are rolling and rolling and rolling, improving the performance of the process. So as you move through, always make sure that you're able to hold on to the improvements that you've been able to experience from your prior change and changes. So that would be the Plan, Do, Study, Act cycle. Here's another brief video that you could take a look at if you want to know a little bit more or see someone else's perspective on this. Often, well, not so often, but an alternative name for Plan, Do, Study, Act is IDEA. And you can see on bottom, investigate the gap between what's happening and what you need. Design countermeasures, that is, plan the changes that you need to make, execute the plan, analyze the results. Let's look at a third one. So now you've seen you've seen Fishbone or cause and effect diagrams. You've seen the Plan, Do, Study, Act cycle. These can be used in isolation. They can be used to work together. And the same thing is true of what's called Pareto analysis or Pareto charts, Pareto diagrams. So it's just a very simple graphic tool. Relative to your statistics course, it would look just like a histogram almost, except that we might not let the bars touch one another because the bars are just different categories of things. Okay, they're not numbers per se. They're just different categories. You'll see that by way of example in a moment. So the Pareto chart graphically indicates which diseases or which problems most affect the process. So if the process is experiencing problems, then yes, go ahead and call those diseases. And the process is infected. So what we're trying to do is remove the infection, so to speak, or reduce its impact. So Pareto diagrams can be thought of very much like a histogram, and it aids organizations in focusing efforts and resources on improving the right thing. So there are a lot of ways that you might see this. I mean, these things, you could see it even as a pie chart. Okay, but the thing about the chart is that the tallest bar, if it's arranged in bars, or the biggest category is the most frequently occurring. The next biggest is the next most frequently occurring, and so on. There's usually some advice that is applied, which is rather than frequency, you might be able to monetize. And sometimes those are the same. But monetization would imply that what you're trying to do is you're trying to prioritize based on some other factor, let's say money, as opposed to just how often something occurs. Because I know that something can occur but have trivial impact. It's not really very important. And it can happen often. Something else can occur, and if it happens once, the impact may be devastating. And so it's relatively common that people who do these things seriously, rather than using just the frequency to determine which bar comes first, and which one comes second, and so on. That we use some other prioritization technique, what I'll say monetization as an example, to say the thing that is the most costly comes first, and you'd have the height of the bar determined by the cost. The thing that's next most costly would come second, and you'd have the height of the bar determined by the cost, and so on and so forth. And in Pareto diagrams or Pareto charts, what you see is that the bars fall in height from left to right, except possibly for the very last bar. And the reason I say except possibly for the very last bar is that it's common that the last bar will just be sort of a catch-all other. There may be 50 different things that fall into that bucket that would collectively make that bar taller than some of the preceding ones. There is a lot of data out there that says that it is easier to reduce the height of one of the early bars by half than it is to reduce one of the small bars by half. And the reason is that in the tall bars, the things that are occurring very frequently or that have big monetary impact, let's say, it's because a lot of times there's a lot of low-hanging fruit that is attached to those, meaning that there are a lot of simple actions that you might be able to take to improve the function of things going on. Okay? Whereas the small ones, those tend to be more nagging problems. The reason that we say things like the devil is in the details. So we focus on first things first, the most important problems. After we've knocked those down substantially, fine. Let's go ahead and focus on the next thing after that. How about SWOT analysis? Most of you are probably familiar with that acronym. Strengths, weaknesses, opportunities, and threats. I usually portray my SWOT diagrams like this. I usually call them SWOT plots for that matter, just because it's easy to remember, SWOT plot. But I would have strengths, weaknesses, opportunities, threats in line this way. So strengths and weaknesses, those are internal to the company. Okay, sorry, those are internal to the company. Whereas opportunities and threats, those are usually, that's an external assessment of the environment. So strengths and weaknesses, those are the things that you have going on inside the company. How do you become better? You make a strength stronger, or you reduce the impact of a weakness. Whereas the opportunities and threats are the things that reside outside the company or outside the control of the company, to a large extent at least. So if it's an opportunity, fantastic. But it's still outside the direct influence of the company, but that doesn't mean that you can't take advantage of it. The same thing with a threat. Who saw COVID coming? However, some companies have been able to take advantage of COVID, at least in some sense. Now, it may sound morbid, but if you think about who's doing well from a business perspective during COVID, apart from a few pharmaceutical companies, it would also be places like mortuaries or places where they are engraving tombstones. And again, that may sound morbid, but it's also true. So what was the threat? The threat out there was something like COVID coming along. But out of that threat, those companies actually had an embedded opportunity. So I would do it that way. So strengths and weaknesses are internal to the company. Opportunities and threats are outside the direct control of the organization. Strengths and opportunities are positives. Negatives are weaknesses and threats. And I would organize that way. Now, what I have inside each of the boxes for strengths, weaknesses, opportunities, and threats are some sample questions that you might try and answer. Because if you try and answer those questions, you're probably going to have a more successful SWOT analysis of the circumstance that you're looking at inside your organization, or even your personal circumstances. Even if you're saying, my marriage isn't working so well, therefore let's do an assessment of our marriage. I have a friend in Ireland that every year for decades, he and his family get away. And they get away for a week and they go to a place where nobody can bother them. And basically that's what they do, is they work on the family and they say, what's going well? What's going poorly? What changes can we make? What safeguards do we have to put in place? So they do a SWOT analysis on their family circumstances and how can it be improved. So this could be applied in so many different ways. It's just that we're used to doing it relative to some business opportunity or challenge. And again, there is a video that's embedded for you on SWOT analysis if you'd like to see a little bit more from someone else's perspective. And then we'll talk a little bit about control charts. Now we're going to talk about that a little bit right now without any examples right now. You see examples in the next lecture. So control charts. They tend to look more or less like this. And their appearance differs a little bit from application to application, from some circumstances to other circumstances, and so on. But basically, they have about 8 lines on them. They have the so-called center line that is at the average performance level of whatever is being tracked. Now, I said that very slowly and carefully, whatever is being tracked, because I might be tracking the mean. I might be tracking the standard deviation. I might be tracking the number of defects. I might be tracking the proportion of defects. I might be tracking the range. I might be tracking lots of different things. So these symbols right here, mu and sigma, refer to the mean and the standard deviation of the thing that is being tracked and charted. Okay? If it's a mean, we usually call it the X-bar chart. If it's a proportion, we usually call it the P-chart. And there are some other types of charts. There are some highly specialized charts. There are some charts that I developed back in the late 80s and early 1990s that were used at NASA, that were used at the National Institutes of Health and places like that. But they were really, really specialized. You wouldn't find them used in ordinary circumstances. Okay, so we will look at just a few common control charts. But there will be 7 lines, 7 main lines. A center line, an upper 1 standard deviation line, and a lower 1 standard deviation line that are positioned quite literally at 1 standard deviation above the mean, 1 standard deviation below the mean. We'll have upper and lower 2 standard deviation warning lines, positioned quite literally at 2 standard deviations above and 2 standard deviations below the center line, or away from the mean. And then we'll have the upper and lower control lines. Those are positioned at 3 standard deviations above the mean, 3 standard deviations below the mean. The 8th line is the data itself. So where these are the values from the first sample, second sample, third sample, fourth sample, and so on, of whatever it is that you're being tracked. So these are literal observed results, actual data. Okay, based on actual data. And we compare the data to the standards. The standards are defined by these values. And by comparing through time, or through sequence, the actual data to the standards, we can see if there's some sort of a change, whether it's change for the better or change for the worse, that is going on inside the process. From an imagination perspective, imagine that you have a normal distribution sitting along the end of this curve, the end of this chart, where the peak of your normal distribution is at the center line, at the mean, as with the other normal distributions that you charted back in your statistics course. So literally 3 standard deviations away, you know you're sitting way out in the tail with the upper control line, the lower control line. That you're setting pretty far out, 2 standard deviations above, 2 standard deviations below, and so on. So you should know what that normal curve looks like and should be able to clearly imagine that residing at one end or the other of the chart. Excuse me. So we have that happening. And with that happening, let's think about some things. If there's been no change in the process so that these lines really represent the actual behavior of the process, then here's what we should know. That about, these are crude approximations, they're crude approximations because having that normal curve sit out there works better for some sorts of charts than it does for others. Okay? Works relatively poorly for some types of charts. But just crudely, if that normal curve crudely describes what's going on, then you know, or you should remember, that half of all values are going to plot, roughly half, above the center line, above the mean, half below the mean. You know that about 2/3 of all values should plot between the upper and lower 1 standard deviation lines. That is, within plus or minus 1 standard deviation of the mean. And of those 2/3, about 1/3 should be in this area. About 1/3 should be in this area. That is about 1/3 of all values should be between the mean and plus 1 standard deviation. 1/3 of all values between the mean and minus 1 standard deviation away from the mean. You know that you should have about 95% of all values within 2 standard deviations of the center line or of the mean. About half that above the mean, about half that below the mean. Well, 95% is 19 out of 20. That leaves only about 1 out of every 20 observations outside of these yellow lines. So up here or down here, only about 1 out of every 20 on average over a long period of time. So that if you see something up here, that's starting to look unusual. Because 1 out of 20 means about half of those 1 out of 20, 1 out of every 40, should be above the upper 2 standard deviation warning line, about 1 out of every 40 below the lower 2 standard deviation warning line. And within plus or minus 3 standard deviations, it's about 0.9973, or about 399 out of every 400 values if the normal actually applies and if the lines that we have here are appropriate. About 399 out of every 400 values would be between the red lines. Only about 1 out of every 400 would be outside the red lines, above the upper one, below the lower one. So about half of the time above the upper, half the time below the lower. Well, what's half of 1 out of every 400? It's 1 out of 800. So if nothing unusual is going on in your process, you should only have about 1 out of every 800 observations up here, and about 1 out of every 800 observations down here. So, you know, what are you going to say if you see something up there, way up there, above that upper red line? You'd say, well, you know, there's a chance that it's just that rare occasion when something is up there and there's no specific cause for it. It's just random. But there is only a 1 in 800 chance of that being the case. There's a 799 out of 800 chance that it wasn't that rare occasion, that instead there's something that caused it. You know, and similarly, we could look for other things that are unusual. So what we do is we tend to compare the track data to these lines for various patterns, and the patterns are defined with respect to zones. So you see these green C's. Between the mean and 1 standard deviation above the center line is zone C. Between the mean and 1 standard deviation below the center line is zone C. Between the upper 1 and 2 standard deviation warning line, that is zone B. Between the lower 1 standard deviation line and the lower 2 standard deviation warning line, zone B. Zone A, from 2 standard deviations out to 3 standard deviations out. Only about 1 out of every 40 observations should be up here. Only about 1 out of every 40 observations should be in this zone A. And only about 1 out of every 800 up here, and another 1 out of 800 down here. So we look for patterns, and those are called Zone C, Zone B, Zone A. I've color-coded those green, yellow, and red because the analogy of a traffic signal works very well for that. Inside the greens, usually no problem. Once you get past a yellow line, that's more or less like a caution light at a traffic signal. And similarly for the red lines, you're talking about maybe 5-alarm fire. Okay, so we use the chart to speak to us. It represents the voice of the data, the voice of the process, to tell us whether something unusual might be happening or not. And if so, the nature of what might be happening. So I've already talked about what's on this slide. So we look for anywhere between 4 and 8 patterns. Now the truth of it is, for the control charts that we'll look at in this course, only the first 4 patterns are applicable, and they'll be on this slide. But there are 4 additional patterns which are applicable for a sort of control chart that is used very, very often, and hence I will go ahead and mention those. But recognize that it's this slide that's going to be important to you. Okay, and while it says pattern analysis test for means, let's just say pattern analysis test, period. PAT 1. It says you have 1 point that plotted beyond zone A, either side of the mean. That means you have 1 point that is either above that upper red line or below that lower red line. Now, for that pattern, when you see that pattern, if nothing else has been happening, that usually represents a sudden and large impact. It's a sudden and large change in the mean of whatever characteristic you're tracking with your chart. Whether it's a sudden or large change in the mean itself, or the proportion defective, or the standard deviation, the variance, whatever it is you're tracking, that usually represents an abrupt and large change in the thing being tracked. That's akin to a 5-alarm fire. Pattern 2 would say, consider that center line, right, the middle green line. And it says your 9 most recent points, 9 points in a row. 9 points consecutively are, let's say, above the line, above that center line. Well, you know, if in fact nothing has happened in the process, there's a very small chance of that. The chance is, oh gee, it's about 1 in 512. You know, that's it, 1 in 512. Similarly, there's about a 1 in 512 chance that as you're always looking at 9 consecutive points, that you'd have 9 consecutive points that were below the center line. So there's all in all about a 1 in 250 chance that if you're looking at the 9 most recent points, you see this pattern. There's only about a 1 in 400 chance you see pattern 1. What does pattern 2 represent? Pattern 2 usually represents a relatively small change that has occurred in the average performance level of that thing being tracked. Mean, variance, standard deviation, range, proportion, whatever that might be. Pattern 3. Well, these charts, the very first charts, were developed back in the 1920s by a man named Walter Schuhart. And they were developed for a workforce here in America where the average educational level of the adult American male was between 5th and 6th grades. Not a lot of math capability, ordinarily speaking. Certainly didn't have calculators, so they couldn't take square roots, couldn't do things like standard deviations easily. So there was a lot that couldn't be done back in the 20s that obviously we can do now, 100 years later. So this pattern has a name. The name is called toolware. And what that means is that oftentimes when you saw it, it was because there was something that was wearing out. But what it really means is an ongoing change in the behavior of the process, whether that is an ongoing decrease in something or an ongoing increase or whatever. I mean, if you use a drill bit over and over and over and over and over time, its diameter is going to get smaller, for example. So if you're looking at diameter of drilled holes and you're staying with the same drill bit, it could be that in fact it's because the drill bit is over time shrinking in diameter. And you'd have 6 consecutive points, let's say the average diameter of the drilled holes, where we sample 5 holes every day, drilled by the same bit, you might see that that was going down over time. But it would require 6 consecutive points falling, or 6 consecutive points rising. Now, we'll talk about these things in much more depth when we have an example, and that'll be in the next slide set, or rather the next lecture. But usually 6 consecutive points that are either falling or climbing. Nothing where it stayed level. They literally have to go up, 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 or down, 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 down. And then pattern 4. Pattern 4 says literally that you have one point is down, the next point is up, down, up, down, up, down, up, down, up, and so on. Alternating up and down points, 14 consecutive ones. Now, when you see that pattern, it's usually one of a couple things. Okay, one is good intentions. And what I mean by that is somebody over-involves themselves in the process. And so let's say the first time they get a result, it's too small. So what do they try and do? They try to adjust the process somehow. Oh, next one's too big. Oh, better adjust. Next one's too small. Better adjust again. Too big, too small, too big, too small. So well-intentioned, but poor result, which is that the person has actually introduced themselves as an additional source of variation in the process. Variation is the enemy here. Variation is not our friend. We're not talking about intentionally introduced variety, like 3 different colors of red, because some people like bright red and some people like deep red. Okay, we're talking about things that are supposed to be the same but are not. Variation. Okay, and so in a case like that, it could be one of the main causes or main sources of this pattern is somebody has over-involved themselves in the process with good intentions of getting closer to being on target every time. Instead, they've accomplished exactly the opposite. And in fact, you will typically see that what happens is that it isn't just up, down, up, down, up, down, that if that's happening, that it'll be up, down, but the variation will increase as you go. Okay. The other typical explanation for this one is that you think you have a chart on one process, but in fact you have 2 different processes. So, you're using 2 machines to produce the same thing, and you think they're performing similarly, but they're not. So sample 1 is from machine A, sample B from machine B. A, B, A, B, A, B. Or first shift, second shift, first shift, second shift, first shift, second shift. Person 1, person 2, person 1, person 2. Things like that. The solution there is, as much as you may want those to be identical, they're not. You use a separate control chart on each. Machine A gets its own chart. Machine B gets its own chart. The first shift gets its own chart. The graveyard shift gets its own chart. Okay, so those are the 4 patterns. These 4 patterns apply literally to any type of control chart that you might encounter. They have something in common, these patterns. They are all rare. Okay, these are 2 really important things. Rare if there's been no change in the process. Meaning that as we move along, if we see 1 or more of these patterns, as we analyze the data, analyze the charts. If we see one or more of these patterns, well, there's some chance that, hey, it just happens now and then. No real explanation, it's just random, right? Natural variation, so to speak. Or something has caused the pattern. Now, because these things are rare, if there's been no change in the process, when we do see them, and when we see these, the likelihood of these patterns is usually somewhere between about 1 in 250 and 1 in 1,000, okay, if nothing has changed. That means that if you see one of these patterns, the likelihood that something has changed is more like somewhere between 249 out of 50, almost certain, or 999 to 999 out of 1,000, almost certain. Okay, so when we see a pattern, we don't automatically assume, oh, it's just random, it happens now and then. Could be, but it's much more likely, assuming we haven't made any mistakes in calculations or anything like that. It is much more common that something's changed, there's an explanation for it. I've told you what those patterns represent, and you're looking for the explanation. So then you become the investigator, not just the analyst, but the investigator that says, okay, what is the source of the change, of the pattern, source of the pattern? And every now and then that'll be something that we intentionally introduce because we think it'll lead to an improvement in the process. We'll talk about that in the next lecture, but many times it isn't. Okay, and then there are 4 other patterns that, if you want to be safe about it, will only apply to something called the X-bar chart, which we're not going to cover in this class. The first 2 of the patterns apply to changes in the mean. The second pattern, 2 patterns, so 7 and 8, pattern 7 and 8, apply only to change in variation. So pattern 5, remember that we have these zones on our chart. Zone C, those 2 zones are within 1 standard deviation either side of the mean. Zones B, those are between 1 and 2 standard deviations either side of the mean, so between the green and yellow lines. Zone C, between the yellow and red lines, between 2 and 3 standard deviations, either above the mean or below the mean, center line. And beyond zone A, which would be anything that is either above that upper red line or below the lower red line. Okay. So pattern 5 says that you've got 2 out of 3 consecutive points. All of those points are on the same side of the mean, and 2 of them happen to be in zone A or beyond. Well, that is a really rare pattern. Usually what that pattern would represent is that you've had a pretty large and pretty sudden change in the performance level of the process, usually with respect to its average, the mean. Remember, this applies to the X-bar chart now. So pattern 6 is similar, but it's not quite as serious. Pattern 6 says 4 out of 5 consecutive points plot in zone B or beyond, all 5 on the same side of the mean. So you have, let's say, all 5 points above the green center line, but 4 of those points are at least 1 standard deviation above. Okay, so that's also rare. So pattern 6, what does that represent? That represents, generally speaking, a pretty, it's not entirely subtle, but it's a relatively small change in the average performance level of the process. Okay? Here's what I can tell you, that the shorter the pattern, shorter the number of points, smaller the number of points in a pattern, the more loudly the process is yelling at you. The smaller number of points required to establish a pattern, the more subtle the pattern. It's more like the process is, as you get a lot of points, it's whispering at you that something is going on. So, for example, with respect to patterns 1, I believe it was 1, let's see if it was 3 or 2. 1, then 5, then 6, then 2. Those all represent changes in the mean. performance, the average performance level of the process. And they all represent changes in the mean. Pattern 1, that was the point that's way out there, either, well, at least 3 standard deviations way beyond zone A. So that one, the process is screaming at you, there's a large and abrupt change. Pattern 5, pretty large change, probably fairly abrupt. Pattern 6, a little bit more subtle change, but it's still a change in the average performance level. Right? 1 point, 3 points in pattern 5, 5 points for pattern 6, 9 consecutive points for pattern 2. Pattern 2 is also a change in the mean, either an increase or a decrease. But since it took 9 points, it's generally a smaller, more subtle change. More points, more subtle. Okay, pattern 7 and 8 reflect changes in variation in the process. So pattern 7, really subtle. Pattern 7 says you've got a bunch of points in zone C, 15 consecutive points in zone C. So they're all between the green lines. Some are above the center line, some are below the center line, but they're all between the green lines. If you see that, assuming that you haven't made any mistakes, you should be celebrating, because this would represent a reduction in the amount of variation in the process. A reduction in the amount of variation in the process, which usually happens only when you have been working on the process for exactly that purpose, to reduce the amount of variation that's going on. Okay. And then there is the opposite pattern. Pattern 7, virtually always good. The other patterns, patterns 1 through 6, they might be good, they might be bad. It depends on context. Pattern 7 is virtually always good. Pattern 8 is virtually always bad. Pattern 8 says we're always looking at 8 consecutive points. Points 1 through 8, 2 through 9, 3 through 10, 4 through 11, and so on. We're always looking at 8 consecutive points. And this would say none of those are in zone C. Some are above the center line, some are below the center line. So, you know, some are bigger than the mean, some are smaller than the mean, but none of them are close to the mean. They are all at least 1 standard deviation from the mean. That's what pattern 8 says. And if that happens, this is almost always a bad pattern, because this almost always represents an unintended, an unwanted, undesirable increase in process variation. Remember, variation is an enemy here. Not variety, variation. So these 4 patterns, 5 through 8, only apply to the X-bar chart, although I can actually force use them in some circumstances on other charts. But generally speaking, let's just say the X-bar chart, which you're not going to see in this class, but patterns 1 through 4 apply to every type of chart. So if you detect some patterns when you construct a control chart, there are some questions that you would naturally ask yourself. And I think on this slide, and probably the next one, maybe even 2 more slides, I have some example questions for you that you would be taking a look at. And that is it for now. So we will finish this slide set next time. We'll do that by moving into this slide. This is about slide 23 for you in your slide set, 23 or 24. And we'll look at 2 specific types of control charts. One called a C chart, which is based on the Poisson distribution, and one called the P chart, which is based on the binomial distribution. So otherwise, thank you very much, and I will see you next time.